It is a quiet afternoon in 1931, in a chemistry laboratory at the College of the Pacific in Stockton, California. A tall, soft-spoken professor named Samuel Stevens Kistler stands over a beaker of jelly, watching it tremble. To most observers, this is unremarkable matter. To Kistler, it is a puzzle that has consumed him for years. Inside that quivering mass lies a question that will quietly reshape materials science. The puzzle begins with a wager. Kistler has bet a colleague, Charles, learned that he can remove the liquid from a gel without collapsing its delicate internal structure. A jelly, after all, is mostly water held inside a fragile lattice of solid threads. Dry it in the ordinary way, and the lattice crumples as the water leaves. Kistler is convinced there must be another path. To understand his obsession, one must understand the gel itself. In the early 20th century, scientists argued bitterly over what gels actually were. Some believed them to be simple emulsions, droplets suspended in fluid. Others, including Kistler, suspected they contained a true solid skeleton, an architecture invisible to the naked eye, proving it required removing the water and leaving the skeleton intact. Kistler's insight is elegant and almost reckless. If liquid water tears the structure apart through surface tension as it evaporates, then the answer is to eliminate surface tension altogether. He proposes pushing the liquid past its critical point, into a strange state where the boundary between liquid and gas simply vanishes. In that supercritical realm, there are no menisci to pull the threads down. The fluid can slip away without leaving a trace. The experiment is dangerous. Kistler must seal silica gels inside a steel autoclave, heat the alcohol within to temperatures above 240 degrees Celsius, and hold it at pressures that could rupture metal. One mistake and the chamber becomes a bomb. But the young chemist proceeds methodically, patiently, swapping water for alcohol, then pushing the alcohol beyond its critical point. When he opens the chamber, the result is astonishing. Inside lies a solid that seems barely to exist. It is nearly weightless, translucent, faintly blue against a dark background, and faintly orange against light. He has produced a material that is more than 99% air, yet retains the exact shape of the gel he began with. Kistler calls it aerogel. In 1931, he publishes his findings in the journal Nature under the modest title Coherent Expanded Aerogels and Jellies. The paper is brief, almost understated, but its implications are vast. Kistler has not merely won a bet. He has proven that gels contain a real, continuous solid network, and he has invented a way to preserve it. He does not stop at silica. Kistler goes on to make aerogels from alumina, from tungsten oxide, from chromia, from tin oxide, even from gelatin and egg white and cellulose. Each one is a frozen ghost of the gel it came from. Each one is among the lightest solids ever made by human hands. The world, however, is not quite ready for him. The early aerogels are extraordinary, but also fragile, expensive, and slow to produce. A single batch can take days of careful pressure cycling. The Great Depression deepens. Industrial chemistry turns toward cheaper, more immediate concerns. Kistler's frozen smoke remains a laboratory curiosity, admired by a small circle of specialists and ignored by the wider world. In the late 1930s, the Monsanto chemical company sees a glimmer of opportunity. They license Kistler's process and begin selling a product called Santosul, a fine silica aerogel powder. It thickens cosmetics, insulates refrigerators, and matters napalm during the Second World War. For a brief moment, aerogel has a commercial life. Then cheaper alternatives arrive, and Santosul quietly disappears from the catalogues. Kistler himself moves on. He joins the Norton Company, then becomes Dean of Engineering at the University of Utah. He works on abrasives, on ceramics, on the chemistry of grinding wheels. The aerogel remains a personal pride, but not his daily work. He dies in 1975, having seen his invention largely forgotten by the wider scientific community. Yet science has a way of returning to its abandoned treasures. In the 1970s, a French researcher named Stanislaus Teichner, working in Lyon, is asked to develop a new method for storing rocket fuels. He rediscovers Kistler's paper. He refines the chemistry, replacing the slow water-glass process with faster silicon alkoxides. Aerogel begins to wake from its 40-year sleep. By the 1980s, laboratories at Berkeley and at Lawrence Livermore are producing aerogels with extraordinary purity and transparency. Researchers measure their properties and find numbers that border on the impossible. Aerogel has the lowest thermal conductivity of any solid. It has densities approaching that of air itself. It is, in essence, a structured vacuum. The applications begin to multiply. Particle physicists use aerogel as a Cherenkov radiator, detecting the faint flashes of subatomic particles slicing through matter. Engineers test it as insulation for cryogenic pipelines. Architects dream of windows that let in light but never let out heat. Kistler's frozen smoke, once a curiosity, becomes a quietly indispensable material. Then, in 1999, NASA prepares a spacecraft called Stardust. Its mission is to chase a comet named Wild 2 and bring back a piece of it. The challenge is enormous. Comet dust travels at speeds of 6 kilometers per second, fast enough to vaporize on impact with almost any material. The engineers need something gentle, something that can catch without crushing. They choose aerogel. Panels of low-density silica aerogel are mounted on the spacecraft like a tennis racket of frozen smoke. When Stardust passes through the comet's tail in 2004, the dust particles burrow into the aerogel, slowing gradually, leaving carrot-shaped tracks frozen in the translucent matrix. In 2006, the capsule returns to Earth with the first samples ever collected from beyond the Moon. Kistler did not live to see his material fly through a comet's tail. He did not see it line the wheel wells of the Mars rovers, insulating delicate electronics against the deep cold of the Martian night. He did not see chemists invent aerogels from graphene, from cellulose, from metal organic frameworks, materials lighter than air and stronger than steel. But each of these descends in some way from his 1931 bet. What makes Kistler's story remarkable is not only the discovery, but its long dormancy. For decades, aerogel sat on a shelf, a solution waiting for problems the world had not yet posed. It is a reminder that scientific value is rarely judged correctly in its own moment. The curiosity of one generation becomes the infrastructure of the next. Today, researchers continue to push the boundaries Kistler first crossed. They produce aerogels that absorb oil spills, aerogels that filter water, aerogels that capture carbon dioxide from the air. Each new variation honors the same essential insight that a structure can be mostly nothing and still be everything that matters. The lattice is the message, the emptiness is the point. It is easy, looking back, to picture Samuel Kistler in that quiet Stockton laboratory, holding a piece of his frozen smoke up to the light. He has won his bet. He has glimpsed something no one has ever seen. He cannot know that 90 years later, fragments of a comet will rest inside his invention, or that rovers will carry it across another world. He only knows in that moment that the impossible has a shape, and he is holding it.